Hey everyone, welcome back to Calculus 1. This will be the 17th lecture of the course, and in this lecture we're going to discuss limits at infinity. And so in the previous lectures we've talked about, we've kind of built up some tools for identifying relative mins and max, relative extrema I guess would be the term we used, and also identifying increasing, decreasing regions. And so we're kind of building towards this, having this ability to sketch curves really efficiently using calculus. And so this section is going to give us, aside from just being analytically very interesting, is going to give us even more power for curve sketching, because what it's going to do, it's going to allow us to infer from the function what happens as the values of x that we plug into the function, as we plug into the argument of the function, get extremely large or conversely extremely small. So what happens as the arguments tend towards infinity or negative infinity. And so that's going to be the subject of this discussion. And so let's go ahead and call this section 3.5, limits at infinity. Okay, so limits at infinity. All right, let's confirm that this is focused nicely. Okay, good enough. All right, so so as I said, in this section we're going to be discussing what happens to a function very far out on the x-axis, or in either direction. And so we'll be discussing what we call the end behavior. That's what the term is typically that is used for this, the end behavior of functions. Right? And sometimes the end behavior has a particular character, and sometimes it has another. And so we'll kind of get into some of the things that can happen with functions as we sort of tend towards more extreme values. So we'll start with an example. So consider the function f of x equals 3x squared divided by x squared plus 1. So it's a rational function. You've got two polynomials. What happens with this function? All right, so as just by way of motivating the discussion, I'm just going to plot this, and we'll see what this one looks like. So the function, so here we'll have 1, 2, 3 on the y-axis, and of course we'll do the same thing here, 1, 2, 3. Okay, the x-axis will be less important here, but one of the things that we'll see that happens here is that this function is going to, it's going to start up here close to 3, it's going to dip down to 0, and then it's going to do the mirror image on the other side. And so this function is an example of a function that's going to tend towards a horizontal value as x grows. So this function tends towards a horizontal value as x grows without bound. Okay, and so we can see it in the plot. I mean, it does definitely look like it kind of levels off here and sort of maybe ends up near 3, but we don't really know what happens further out. I mean, it just kind of looks like it in this very narrow plot. So numerically, let's just take an example. Let's plug in some values here and see what happens with this guy for some relatively large values. So we'll say negative infinity out here. Of course, we can't plug that in. But what about at negative 100, negative 10, negative 1, 0, and then the other side as well. So this is a common thing that we've done this before, right? Just when we were discussing limits initially. Right, so if we were to plug these values into the function, what do we get out? Like what is the value? What does the function evaluate to at like negative 100? Well, at 0, the value of the function is 0, right? You can see that if you plug in a 0, you get a 0 in the numerator and a 1 in the denominator, so you get a 0. Now, when you plug in negative 1 and positive 1, now notice the arguments are squared, so negatives, and you can see it in the plot that they mirror each other. So negative values will have the same value as their corresponding positive input. And so when we plug in 1 and negative 1, we get a 1.5, 1.5, and that kind of bears out here. It's right about there-ish, right about there-ish. When we plug in 10, we get 2.97 approximately, and 2.97 approximately, right? And so this would be like kind of the edge of what you would feasibly plot like on graph paper like this. But what happens when you plug in like negative 100 or positive 100? Well, what you'll find is that the function evaluates to something like 2.9997, something like that. Okay, approximately, right? So you can see that this is an order of magnitude larger, but the function didn't blow up. It simply went from 2.97 to 2.9997, so very, very close in value. And indeed, when we look at this analytically, what we'll identify is that no matter how large the value you plug in, the function never exceeds the value of 3. And so what you might be able to say here is that as you get as you get further and further out on the x-axis in either direction, the function gets closer and closer to a value of 3. Okay, and so the way we would denote this, so this is the characteristic of a limit, right? Of an asymptote at a limit. And so what we might be able to say, so the way we would denote this idea of a limit, a horizontal at infinity, would be to say something like this: the limit as x approaches infinity of 3x squared over x squared plus 1 equals, in this case, 3, right? And then the same thing for x approaching negative infinity. So the function has the same value, approaches the same value as the inputs grow without bound and as they conversely shrink without bound. Okay, so this is kind of a motivating example, and this guy here, this value of 3 in this function, would be what we would call a horizontal asymptote. So we've certainly seen vertical asymptotes. In this case, this is an example of an asymptote that is horizontal. And the idea being that the function will approach this value but never precisely equal it, and will never cross it. It'll just get ever increasingly close to it. Okay, so let's define this idea of limits at infinity a little bit more precisely. Okay, so let L, which is going to be our limit, be a real number, so it's a real valued limit. Okay, so then we'll kind of have one for positive infinity, one for negative infinity. So the first one would be to say the statement limit as x approaches infinity of f of x equals L means, what does it mean? It means that for each epsilon greater than 0, so this is again some positive quantity, some tiny positive quantity, there exists an m greater than 0 such that f of x minus L is less than epsilon whenever x is greater than m. Now m can be I think typically people take m to be like a natural number, so an integer. But m can be in this context, m can be could be a real number, but it wouldn't be much sense in it being a real number. It's harder to work with. It'd be better that if it were just an integer. But the idea here is that like you give me an epsilon, right? So some tiny number, 0.00000, maybe 50 zeros in it or something. But it's a positive quantity, and you say, hey, look, I want to know how far out do I have to go before the value of the function is within epsilon of whatever the limit value is. And if L is the limit of the function, then I should be able to go and find some integer m such that the function is indeed within epsilon of L for any x larger than m. Okay, so it's a similar concept to like the limits that we talked about previously, but this one is this one is a little different because it's basically a limit at infinity, right? So that's where you have for all m greater than 0, right? So and then the same thing is true of the limits at negative infinity. And so the way that would the way we would write that up would be to say the statement limit as x approaches negative infinity of f of x equals L. All right, so what that means is for each epsilon greater than 0, there exists an n, here again taken to be an integer less than 0, such that the absolute value of the difference between f of x and L is less than epsilon whenever x is less than this particular integer. So the only thing, so this is the exact same idea basically, except now you're saying that this has to hold for all x less than n, of course, because we're on the negative side of the number line, right? So there's going to be some m out here, or sorry, n in this case. There's going to be some n for which any x further out, when evaluated inside the function, will be equal to or will be less than epsilon. Okay, so f of x minus L will be less than epsilon for any x that is further out in the negative direction on the real number line. Okay, so we're not going to make a lot of use of the definition. This is Calculus 1, but just know that it's the same idea. It's the same idea as what we saw with our limit theorems early on in Calc 1. Okay. So the opening example that we had, I think it was f of x equals 3x squared over x squared plus 1. So this opening example. So this is an example in which the graph of f approached a horizontal line, and we dubbed that a horizontal asymptote. So this example has a horizontal asymptote at x equals 3, right? And we said there that the limit as x approached infinity of 3x squared over x squared plus 1 was equal to 3, which is the same for actually the negative direction as well, right? So this is an example of a horizontal asymptote. Okay, and so let's define that with a little more rigor as well. So the line y equals L is a horizontal asymptote of the graph of f if, okay, now if what? Well, if the limit as x approaches infinity of f of x equals L, or the limit as x approaches negative infinity of f of x equals L. Right? So one or the other, or in the case of our example, both. So maybe you could say and or. Okay. So that's the definition of the limit of the horizontal asymptote. So basically, the idea of a limit at infinity and a horizontal asymptote are identical. So they coexist, right? They depend upon each other. So it follows from this definition, right, of course, that basically any function f would have at most, right, 2 horizontal asymptotes, right? So any function f will have at most 2 distinct asymptotes, right? It may be the case that the limit as x approaches infinity of f of x equals L, and the limit as x approaches infinity of as x approaches negative infinity of f of x equals k, right? So L not equal to k. So that happens quite often as well, right? So, but there's no additional possibility, right? So as the function grows without bound, it maybe approaches a value, and as the function decreases without bound, it maybe approaches the same value or possibly a different value. But there's no other way that the function, there is no other option for a horizontal asymptote. Now, you should, I mean, so maybe that's really obvious from the definition, right? But just contrast that with the idea of vertical asymptotes, right? For example, f of x equal to tangent of x has infinitely many vertical asymptotes, right? So it's possible for functions to have infinitely many vertical asymptotes, but only 2 or fewer horizontal asymptotes. Okay, so just something to note, right? So remember, if you recall the tangent function, right? So if that's 0, right? So it has asymptotes every pi radians, right? So it kind of looks like this. Does the same thing over here, right? It just does this to infinity, right, as you move out on the x-axis. So it has infinitely many vertical asymptotes. Okay, just a review, just a reminder there. Okay, so the nice thing about limits at infinity is that many of the same nice properties hold, the nice properties from regular limits. So for example, so let me write that, many of the same properties hold for limits at infinity. So a couple of examples would be that the limit as x approaches infinity of a sum like this, f of x plus g of x, you can break the limit up like so. So that's true of limits at infinity. Another property that we liked before was the product of two functions. Can be broken up like so. Okay, so that's nice. Okay, and others as well. We won't rehash them all, but you can go back and confirm those. So we're gonna kind of move next into like a sort of a a flurry of theorems and examples that'll help us to come up with some general properties of, well, these examples kind of will be useful in building some sort of a general framework for evaluating horizontal limits, or identifying what happens with functions as they approach infinity or negative infinity. And so there's kind of a flurry of them. They somewhat can seem unrelated, but you'll see in a moment that they all are very closely related. So the first one is this. So if R is a positive rational number, and C is any real number, okay, then the following is true. So the limit as x approaches infinity of the constant over x to the r power is 0. Okay, and similarly, the limit as x approaches negative infinity of c over x to the r is also 0, right? So what is this saying? So c is some number, right? So like an example function might be something like this, f of x equals 5 over x squared. For example, 5 is some constant, x is in the denominator, and it's exponentiated, it's squared, and obviously 2 is a rational number, right? So basically the idea here is that as x grows without bound, the size of the denominator is going to grow without bound, and you're going to always have some finite number divided by some number that grows without bound. And so anytime you have a small number divided by a really large number, you're going to get something extremely small. And as x goes to infinity, then this is going to go to 0. Okay, so hopefully that's like really intuitive, and of course, the exponent on exponent r can be, a rational number, properly speaking, as well, not a whole number like 2, but like 3/5 or something, or 7 halves, whatever it happens to be. So yeah, and so this is also, of course, this theorem is also assuming that x to the r power is defined when x is less than 0. Okay, that's for this other piece. So x to the r needs to be defined when x is less than 0, right? So not a problem. Most examples, that's kind of obvious, right? Okay, so that's the first one. So just basically the key here is that any constant divided by something that's growing without bound is going to naturally have a limit of equal to 0. Okay. Now another one that we'll need here is the following. The limit as x approaches negative infinity of e to the x is equal to 0, and the limit as x approaches infinity of e to the negative x is equal to 0. Okay, so this one, the idea here would be, so if I plug in some negative value for x, I evaluate e to some negative exponent, then I'm dividing 1 over whatever e, to raise to the exponent happens to be, right? And so as that grows, as that denominator would grow, right? So, okay, hold on. So if f of x equals e to the x, and so if I plug in a negative, just to make sure this is clear, like -5, then I get e to the -5, which is 1 over e to the 5th, right? So this kind of basically boils down to the previous example. You've got a constant up top of 1, and the denominator is basically a constant raised to some exponent, right? And then that exponent is growing without bound here. In this case, it's decreasing, heading towards negative infinity without bound, right? And in the case of this other one, right, if f of x equals e to the negative x, right, so then f of f of 5 would equal, because right, x is on the positive side, it's heading off to positive infinity, so I'd plug in positive values here. Then it's going to be e to the negative 5 again, and again it's 1 over e to the 5th. And so again, the exponent is what's growing, right? And the exponent is always negative, meaning it's 1 divided by whatever that quantity happens to be. So this is just sort of a special case that we'll need for a couple of nice examples. But basically the idea here is that it's the same as the previous example, right? If the exponent on the here is negative, then this thing is headed to 0, right? Okay. Let's do an example of this one. So let's do an example real quick here. So let's evaluate the limit as x goes to infinity of 5 minus 2 over x squared. Okay, so this is like the previous theorem, right? So the limit as x goes to infinity of 5 minus 2 over x squared. Well, again, we can use those properties of limits and we can break this one apart. X goes to infinity of 5 minus the limit as x goes to infinity of 2 over x squared. So this is just constant, right? All right, so where does this head off to? 5. What happens here? Well, this is the exact thing we just talked about, right? So this denominator is going to grow without bound, and you're going to be taking 2 divided by a larger and larger and larger number successively. And so as x goes, you know, all the way out, then the value of this is going to drop to 0, right? And so this guy heads to 0. And so what you could say is that this is going to be equal to basically 5 minus 0, which is 5, right? So this limit would be 5, right? So this function here has a horizontal asymptote at x equals 5. Okay, so good example there. Let's do one using the exponential. So another example, let's evaluate the limit as x approaches infinity of 3 divided by e to the x. Okay. So the limit as x approaches infinity of 3 over e to the x. Well, you could leave it like this and it's fine, but if we want to explicitly make use of the theorem we just talked about, you could obviously notice that this is equal to 3 times the limit as x approaches infinity of e to the negative x, right? And so, you know, this is going to be 3 times, I mean, what's going to happen here, right? I mean, I actually think it's clearer if you like sort of look at it like this, but if you look at it like this, then obviously you're plugging in positive values of x into this, so this denominator is going to get larger and larger and larger, you know, or conversely, you could say this is 3 times 1 over e to the x, and, you know, again, the denominator is going to grow without bound. You're dividing a finite number by a number that's growing without bound, so this is obviously going to head off to 0. So that's a good example. Okay. What about, here's an example. Let's consider, let's try to evaluate the limit as x approaches infinity of 2x minus 1 over x plus 1. Okay, and we could think of that as being kind of like this, right? You've got the polynomial on the top, you know, and that's going to have its own limit, and then you've got the polynomial on the bottom, which is going to also have its own limit. Right, now what are those limits going to look like? Well, when you think about it like this, this one is obviously just a polynomial. 2 times a really large number minus 1 is, you know, going to head off to infinity, right? What about the denominator? Well, you're going to get the same thing, right? You've got some very large number plus 1, right? And as x gets even larger and larger, then clearly the value of this is going to get larger and larger. And so this is what we call an determinant form. Meaning this isn't helpful. Infinity divided by infinity doesn't really tell us anything. Okay. So I mean, is this so this is what's called the indeterminate form. But the reality is that this does have a limit, and what we need to do is we need to get creative here a little bit. We got to get creative with how we evaluate this limit. Okay. And so one of the things you can do here, this is a trick, a little algebraic trick to see what's really happening in the expression overall as x grows to infinity. Let's rewrite it here, 2x minus 1 over x plus 1. Okay, so what we can do is we can rewrite this as the following. So the limit as x goes to infinity of, right now up top you could write 2x minus 1 over 1, and in the bottom you can write x plus 1 over 1, right? Perfectly legitimate, although a little messy and a little bit out of context. It'd be like, why would you ever do this? But then what we can do is we can say, well, okay, we've got this guy here that looks pretty ugly, but an idea maybe would come to us to say, let's see if we can deal with this x. The problem happens to be the x, right? So what if we multiply top and bottom by 1 over x? Like so, right? Just simplify that a little bit to see what that looks like. So you'd have 2x minus 1 over x divided by x plus 1 over x. Now, one of the things you can see here is that you can do like some cancellation here, kind of break this up. And so you could write it like this, 2 minus 1 over x, right? So just canceling the 2's and breaking the fraction up, divided by 1 plus 1 over x. Okay? So, these are just algebraic tricks, right? We're just, reinterpreting this rational function as, pretty straightforward little trick here, and then multiply top and bottom by the same thing. Totally doable, totally legal. And then doing a little cancellation and writing the function in a way that is very inconvenient under normal circumstances, but when you're evaluating what happens to the function for extremely large values of x, this is way more useful, because right now if you do the same exercise where you take the numerator limit separately and then you take the denominator limit separately as well, well, what happens here? So the limit as x approaches infinity of 2 is just 2. And of course this, we know, goes to 0, right? 1 divided by an increasingly large number, the number growing without bound would be 0, right? So 2 minus 0 up top. And in the bottom, we would get something kind of similar, right? So it'd be 1 plus 0, right? So 1 plus 0. And that's great, because now you have 2 over 1, and you can see that the limit actually here is 2, right? It's not infinity over infinity, right? It is an actual finite number. All right, so what does this function look like? Let's draw it. Let's see if we can get a reasonably good picture of this thing. So say it goes through there, and as we've seen, it does have a horizontal asymptote at 2, and so it also has a horizontal asymptote at it has a vertical asymptote at x equals 1. Right, so you're going to have something here as well. And what you'll see is that the function kind of comes up like this, and then as it heads off, as x values grow towards positive infinity, the function gets increasingly ever so close to the value of x of f(x) equals 2 here, right? So, well, I should just say y equals 2, or y, right, f of x. So this is the side that we were concerned with. So it comes up, it's hugging this asymptote y equals, or x equals 1, and then it comes up and it kind of switches. It's sort of like takes a hard right turn and then becomes asymptotic against y equals 2. And the function actually over here is doing something between those two asymptotes. So that's what this function looks like if you were to plot it. Okay, so this idea that the limit as x approaches infinity of the function is 2 indicates this horizontal asymptote here. Okay, good. So this technique here is a very useful approach when dealing with horizontal asymptotes, limits at infinity, particularly of rational functions, obviously. So let's do some more examples just to make sure that that's really firmed up. So what about evaluate the limit as x goes to infinity of 2x plus 5 over 3x squared plus 1. What happens here? Well, let's try the same trick. Let's try that same trick again and see what we get. So here you'll notice that you have two, the degree of the numerator here is 1, right? It's the first degree. And the denominator, the degree is 2. So something a little different already is happening. So we'll multiply top and bottom by 1 over x squared. Okay. And so what happens when we do that? Well, we get something that looks like this. So it'd be 2x plus 5 over x squared divided by 3x squared plus 1 over x squared. All right, and you can see that the numerator, the cancellation doesn't quite work, right? So you actually end up with 2 over x plus 5 over x squared, right? When you cancel an x here, one of them's left for this piece. This should just be an x. It looks kind of funny, but in the denominator we do in fact get this 3 plus 1 over x squared form. And so what happens here when we evaluate these limits? Well, the denominator is 3, right? 3 plus, and this heads to 0. But the numerator, we don't get that, right? You still have 2 divided by a number growing without bound, and so this is going to be 0 plus 0. So you ultimately get 0 in the numerator. So that's what happens with this one, right? So notice here that the degree is 2 in the bottom, and in the top the degree is 1, right? So the degrees they're not the same. So let's see if it has anything to do with the square. I don't think it has anything to do with the square, right? The problem is more likely that we can't use this trick in this, and we don't get the same idea. We're not able to move all of the x's out of this term, right? Let's try another example though. Let's evaluate the limit as x goes to infinity of 2x squared plus 5 over 3x squared plus 1. All right, so here the degrees agree, and we get, well, let's rewrite it. And so here we can use the trick. We can divide everything by x squared, and we would get 2x squared plus 5. I'll just be a real stickler and rewrite everything. 3x squared plus 1 over x squared, right? Just so you can see that these will totally cancel, those will totally cancel. And so you end up with the limit as x approaches infinity of 2 plus 5 over x squared divided by 3 plus 1 over x squared. And so you get 2/3, right? The leading term, these terms out front here are what ends up staying. The rest head off to 0, right? So this goes to 0, that goes to 0. So are we seeing a pattern yet, would be the question. Let's try one more example. Are we starting to get an idea for maybe what the pattern is? If we aren't, this last example will probably solidify it. So what happens if the numerator has a larger degree than the denominator? Let's evaluate the limit as x goes to infinity of 2x cubed plus 5 over 3x squared plus 1. So now we're dealing with a third degree in the top, second degree in the bottom. And so I'm just going to try to teach good math habits by just kind of rewrite the thing. Don't be afraid to rewrite it. So often students make mistakes when they're evaluating these things because they don't write their steps down. They just kind of try to do too much in their head. So I always try to do it the right way. But so in this example, we can divide x squared out of everything. And so what happens if we do that? We would get a, let's see, so it'd be 2 the limit as x goes to infinity, 2x cubed plus 5 over x squared divided by 3x squared plus 1 over x squared. Right, and that's going to be the limit as x approaches infinity of, well, here you're stuck with a 2x plus 5 over x squared, and down below you do get the 3 plus 1 over x squared. And so that's okay. So the bottom you get the 3. Well, what happens up here though? Well, I mean, this is going to grow without bounds. That's going to grow. This one's heading off to infinity. That's heading off to 0. So you get infinity plus 0. So infinity over 3, which is infinity. So this guy here, in this case, and hopefully this is intuitive. Like the only terms that really matter are these, right? This one's going to get big, clearly, but this one's going to get big a lot faster, right? And so that's kind of the secret here. That's the key, right? So this one is going to ultimately, as x grows without bound, this is going to wander off towards positive infinity. Now, in this case, we wouldn't say that the limit is infinity. We would, well, sometimes you would just sort of, casually write it like this, but we would really say that the limit doesn't exist. Right, because this one is, infinity is not a real number. So that's that. Okay, so those examples hopefully kind of will more or less tell you what the following theorem is about, but if not, they will certainly motivate it, and as we get into it, it'll be kind of clear why these things are true. So this is kind of a theorem to summarize what we just talked about for these rational functions. So we'll let f of x equal p of x over q of x be a rational function. Okay, so let f of x equal p of x over q of x be a rational function. And so rational doesn't just mean a ratio of two things, it means a ratio of two polynomials, right? So these are both polynomials. Okay, if the degree of p is equal to n and the degree of q is equal to m, then a couple of things are true. First, well, if n is less than m, okay, so if the degree of the numerator is less than the degree of the denominator, then the limit as x approaches infinity of f of x equals 0. That's the first piece, right? So if the degree of the numerator is less than the degree of the denominator, then the function overall will tend towards 0 as x gets larger and larger. And so that's the example we saw first, right? That's this guy. Here we go. Right, so here we saw that the degree here is 1, the degree here is 2, right? And so when we get down here, we can see that this guy here is going to be 0 plus 0, but this one is going to be some kind of finite number. right? And in that case, 0 divided by any finite number is 0. All right, so that's the first example we saw. And so this just kind of generalizes it and makes it clear, more general, right? Now the second case would be what happens if n is equal to m. So that was the very first example we looked at. If n is equal to m, then the limit as x approaches infinity of f of x is equal to some ratio a over b, right, where a is the leading coefficient of p of x and b is the lead coefficient of q of x. Okay, so this term lead coefficient, that means the coefficient on the term with the largest exponent. Okay, and so we saw an example like this as well. So right here, for example, right, so here the degree is 2, and here the degree is also 2, so they're the same. And so the limit ended up being 2/3, which you can see is the ratio of the lead coefficients. Right, the leading coefficients would be 2 on the top and 3 on the bottom, so 2/3 is what the limit turns out to be. And this is just that clear example of, you know, this kind of trick, this algebraic trick coming into play here. Okay, so in the case of the numerator and denominator having the same degree, then you get the limit at infinity being the ratio of the leading coefficients. Now what happens if n is greater than m? So if n is greater than m, then the limit as x approaches infinity of f of x, well, we said informally it's infinity, i.e., but we would say i.e. the limit does not exist. Okay. All right, so that's the big nice theorem here, and this applies for polynomials. Now, this same sort of thing happens all over the place, actually, you know. So let's do an example that doesn't involve polynomials, but where we see the same kind of thing occurring. So consider the logistic function. Some of you may or may not be familiar with a logistic function. F of x equals 1 over 1 plus e to the negative x. Okay, this function is very, very famous. So this is called the logistic function. So the logistic function actually has 2 horizontal asymptotes. Okay, so let's figure out what they are. So what is the limit of the function as x approaches positive infinity? Well, again, we can kind of break this all up. Right, and then I can move the limit into the denominator here as well, and I can also break it up, right? So I'm going to kind of just do that in one step. Okay, now what happens here? Well, this one is obviously 1, right? And what happens down below here? Well, this one is obviously 1 as well. And what happens here? Right, this is the one where we saw the theorem, right? We saw what happens is we're plugging in positive values for x, but x has a negative sign in front of it, so this is going to be e to the negative some number, right? E to some negative exponent. So it's really 1 over e to the x power, right? And so this guy is, the denominator here would grow to infinity, and so it's 1 over that, right? And so just to make that clear, I just want to make sure people understand this. This is like 1 over e to the x, right? And so this is going to grow without bound. This is obviously fixed. And so this is going to head off to 0. which means that the limit of this function as x approaches infinity is 1, right? 1 over 1 plus 0 is 1. Okay, so that's what happens on the right-hand side of the number line for this guy. What happens on the other side? Well, what happens when x approaches negative infinity? All right, let's see. So again, same technique here. We want to consider the numerator and the denominator separately. Okay. Well, so again, obvious what happens in a couple places. This is clearly 1, and this is also clearly 1. But what's going on here? Is this going to 0? Is this going to infinity? Well, again, we want to think about what this is. X is approaching negative infinity, and this is e to the negative x. So it's like 1 over e to the x. So if I'm plugging negative values in here, what is going to happen here? Well, in this case, it's actually probably easier to think about it like this, right? If I plug in like a -2, for example, a -2 is a +2, so this becomes like e squared. If I plug in a -10, it's like e to the 10th power. If I plug in, -1000, this is e to the 1000th power, right? So this piece here, right, similarly here, these are both heading to infinity, right? They're getting larger and larger. So that's what you have here. So this is like 1 over 1 plus infinity. So it's like 1 over infinity, which is 0. Okay. So you always have to think about what values of x am I plugging into the function on the extreme end, right? So here I'm always going to be plugging in negative values as x gets, further out, right? And it's a negative value, so it's like a positive value. Okay. And so that term basically means it heads off to infinity, just that piece of it. So then overall you have a 1 in the numerator divided by something that's growing without bound in the denominator, so the overall limit is heading to 0. Okay, so to summarize the logistic function, the limit as x approaches infinity of 1 over 1 plus e to the negative x was 1, and the limit as x approached negative infinity of 1 over 1 plus e to the negative x was 0. Okay, now what does this function look like? It looks like, it kind of basically looks like this. You've got a horizontal asymptote here, and it hugs the x-axis. Okay, it hugs the x-axis, and it cuts through right in the middle, and then it hugs the y-axis. So it kind of does one of these. So this would be y equals 1. So there's your y equals 1 asymptote, this one. And then you've got your y equals 0 asymptote as well. So that's what this function looks like. All right. Okay, now what about, let's talk about, functions that don't have, an example of a function that doesn't have any horizontal asymptote. So let's look at like f of x equals sine of x. And so we know that the sine function, right, it starts at 0 here, and it goes like this, right? And it just keeps going. And the same thing on the other side, right? And so it kind of tops out at y equals 1, bottoms out at y equals 2, or sorry, y equals -1. Right, but the behavior is it just clearly oscillates from positive infinity to negative infinity, and the entire time it's perpetually in oscillation, right? So it never gets infinitely close to any value and stays there, right? So this is an example of a function where there is clearly no horizontal asymptote, right? There's no horizontal limit, and so the limit as x approaches plus or minus infinity of sine of x, we would say does not exist. Okay. This is just because it goes up to 1 and then it goes down to negative, and then it goes back up to 1 and back down to negative 1. It does this forever, right? Never deviates from that. Okay, so this is just one of many examples, but sometimes the sine function does, in some cases, the sine function maybe does do something different. Let's consider this one. Let's identify the limit of x approaching infinity of sine of x over x. Okay, so this, I think we talked about this one previously. We talked about this function as but not as x approach infinity, but I think as x approach 0, if memory serves. So we know, so here's what we know. We know that -1 is less than sine of x, which is less than 1, right, for all x greater than 0, right? So we know that for all x to the right-hand side, this is true, right? And so we also know, therefore, that -1 over x is going to be less than sine of x over x, which will be less than 1 over x for all x as well, right? Just dividing everything by x, and x is a positive quantity, so no problem, right? So don't have to flip the inequalities or anything, but if you divide -1, so just dividing everything by x, a positive x. Now we know these two limits, we know, right? So we know that the limit as x approaches infinity of -1 over x is 0, and that's also true for this other one, right? Okay, so that's true. Now, if sine of x is between, this should be less than or equal to also, right? So if sine of x over x is between these two values, is sandwiched between these two values for all x, then it follows, right? So it follows using the, what do we call it? The squeeze theorem, right? So it follows from the squeeze theorem that the limit as x goes to infinity of sine x over x equals 0 as well. Right, so this function does have a limit, right, at infinity, and it's 0. Okay. So these are just a few examples. Many functions really do not, in general, functions do not approach finite limits as x approaches infinity, right? So clear example, it does not go to some L as x goes to infinity, right? This one clearly diverges to infinity, right? So f, takes off to infinity as x gets larger and larger. So what do we mean when we say that a function's limit at infinity is infinity, right? So you might write that the limit as x approaches infinity of x squared is equal to infinity. So what do we mean by that? Well, let's get a definition out here. So this would be a limit at infinity that's equal to infinity. So let f be a function defined on the interval a to infinity. Okay, so basically the right hand side of the number line, of the real number line. then what do we mean? Well, the statement that the limit as x goes to infinity of f of x equals infinity means that for each positive value m, there is a corresponding number n greater than 0 such that f of x is greater than m whenever x is greater than n. All right. So this is exactly the same theory. This is the almost the exact same articulation that we saw as the one that we saw back in our early discussion of limits, right? What does it mean when we say that as x approaches a finite number a, that the value of the function goes to infinity, right? This is the case. That was the case of like asymptotic behavior, vertical asymptotic behavior. So here what we're saying is that, hey, look, if you give me some extremely large number, like 10 billion or something, I'm going to be able to find some x, some n that's, some positive number n, such that the function is larger than 10 million for every x larger than whatever n I've chosen, right? So basically, all this is saying is that the function gets increasingly large beyond a certain point. It's always larger than whatever value you give me. Okay, and the reverse statement we'll write down as well. It's very much the same, right? So not the reverse statement, but the other case of the limit being negative infinity. So limit as x approaches infinity of f of x equals negative infinity means that for each negative number m, there exists a corresponding n less than 0 such that f of x, the function evaluated x, would be less than m whenever x itself is less than n. Okay, so same idea, right? But here we're just on the negative side. Oh, I'm sorry, x greater than n. Yeah. Right. So here's our function, right? So if you give me some negative value m, and you say go find, and the function kind of does something like this, all I got to do is go find some n out here such that the value of the function is below m for all x greater than n. So all these x's out here, they all produce values of the function that are further down than m, right? They're closer to negative infinity than m, if that's even probably not an appropriate way to say that. But. So that's the idea here. And again, these are just technical definitions. These will be important, if you ever move into the more rigorous real analysis coursework. But right now, hopefully these are just intuitive. I wouldn't expect people to be able to use them too much, or even really want to at this point. But the idea here is just hopefully that there is a more technical definition of this, and also kind of having it defined justifies usage of the term limit as x approaches infinity of f of x equals infinity, right? So you just being able to say that when because this is not a real number, right? So this is not strictly speaking true without a definition like the one we just went through, right? And same, so you'll be able to say things like this as well, right? Or any combination of these things, right? I guess there's just one more. I might as well write it. Okay, so these are all kind of covered by this most recent definition, right? So these would be limits that are not real numbers, limits outside the real number set. So, okay, that's where we'll let off for this lecture, and the next lecture we'll get into, basically we'll kind of consolidate all of our curve sketching machinery and do some examples of using kind of all of the techniques together and using them, in a coordinated way to get really nice sketches of curves without having to plot anything. Okay, we'll see you then.